Hey,
Hi.
hi.
Okay. Interesting. Okay. So we wait for maybe 1 more minute until it's exactly 05. Okay. Let me I see. Okay. So yeah, this first of all, this lecture is being recorded. Okay, so I'll upload that onto Moodle. Uh so let me share with you what is being posted onto Moodle. So let me share the screen first. So as you can see, all the exercises are there and all the solutions are there. So in today, I'll talk about the seminar and for Group 1 students. So it will be exercise 10. Uh, as you can see, there's also exercise 11. So I didn't provide any upload link because this is basically for uh, what you to do your own. Okay, so this is the exercise on our last lecture, which I'm going to talk about. So obviously this is last week, so we cannot really talk about that. And so I have included solutions as well. So for Group 1 students, if I have time after talking about exercise 10 and some of the remaining questions, exam questions, the main point of exam questions that are in exercise 9, then I'll talk about exercise 11. Otherwise, please post your questions on the discussion forum that not many people have used, unfortunately. So please do that and or drop me an email. So over the past 2 months, there are several students that drop me email. So yeah, I'm very happy to answer the questions actually. So do that and discuss with your peers how to do these questions. So exercise 11 is basically the for the questions that I'm going to talk about today in mainly matrix factor model. Okay, because it's a very new topic and it's very easy to get into very difficult computations. So I will not go very deep, but only conceptually and the procedure in solving for matrix vector model, how to find estimators and so on. Okay, and what's the usage? What are the some concerns of matrix vector model? So that's today's lecture, and that's exercise 11. So that's the first thing I want to talk about, and so let's go back to our lecture. And if you have any questions, let me know. Okay. So you can show your face and you don't need to show your face. Just shout, have a shout and no, let me know what questions you have. Okay. Um, let me share back the let me share back the screen for the writer. Am I sharing? Okay. So so let me start a new page. Do remind me if you don't see anything that you expect to see. Okay, so it could be that I do not remember to share. Okay, so last week we have talked about all the factor model, how to find the estimators for factor models. So we have gone through a very lengthy derivation and also the number of factors, which is actually quite intuitive, I would say, because after all, we're doing PCA. Remember, in the last lecture, we talked about time series factor model really is the PCA for the sample covariance matrix for your observation, basically. Okay. And finding the number of factors is basically finding the number of significant eigenvalues in your sample covariance matrix for the time series data. Okay. So, uh, so of course you need to remember how to do the derivation. Okay. So this is in the last lecture. And in this lecture, so we'll start with a new topic, so which is the matrix factor model. So obviously this is the last part of the last chapter, the matrix factor model. Okay, so this is basically to engage in the fact that we have more and more time series data which are high dimensional in nature. High dimensional, uh, not even in the usual sense of a very large dimensional factor, but actually is structured. High dimension, but with a structure. So now, matrix time series is high dimension at the same time is a structure. Of course, is basically a rectangular uh, array of time series data. Okay, so where do you usually see this kind of data? So in the last lecture, we talked about application where you have a 10 by 10 time series. So basically 100 time series structured in a 10 by 10 matrix of portfolio returns. Okay, so each cell of this 10 by 10 data represent different size and different book to market ratio range. Okay. So, and all these data are actually within the Pharma and French website, which I've shown you in the last lecture. These are also in your lecture notes. Okay. So I click some of the link in your lecture notes and it directly go to that web page of downloading that 10 by 10 portfolio return data. So, apart from this 10 by 10 portfolio data, so when can you expect this kind of matrix factor model? Well, usually, uh, because of my expertise, so I usually deal with financial data and as well as economic data. So these usually come with very structured data, usually by countries or by company. So each row can represent different countries or different companies. So represent different countries, and then the columns can be different micro or macroeconomic indicators. Okay, so you can download this data very easily from the OECD webpage. OECD provide lots of these data, so different countries' GDP, maybe even different regions over the G20 countries and consumer price index, production index, etc., etc. All the macroeconomic indicators. They are in the columns. Okay, so you have a row, different rows and different columns. So it's of course matrix time series data. So these data are very common. Okay, and it's obviously structured. Okay, each row represent different countries. Each column represent different economic indicators. Um, in the last lecture, we talked about can we actually stack these together? And the answer is, of course, you don't want to because, after all, it's a matrix. Okay, so we want to analyze this respecting it comes from a matrix. Okay, so The matrix factor model I want to talk about is satisfy this purpose. So it try to do dimension reduction as in what we have seen in the factor model. At the same time, respecting that it originally comes from a matrix data. So in the end, it's still matrix data following different a certain factor structure. Okay. So this is the basically the background, and we will at the end of the day see some examples. Okay, so let me switch on my R Studio as well. Okay, so I hope I'm still sharing this Microsoft whiteboard. So to make sure I stop it and then share it again. Okay, so let's start with I do not have too much notes to take. So because so that's page one. So we'll talk about the matrix factor model, of course. So the topic's matrix factor model. Okay. So what is matrix factor model? So when your time series, so when your xt uh is such that so xt is of course a matrix. Let's say this is p by q. So in terms of the examples I've given, so P is the number of countries, Q is the number of micro or macroeconomic indicators, or different companies. P is the number of companies you're looking at, or different stocks you're looking at. Q is the number of company indicators. So there are lots of indicators for so returns, volume traded for that stock, um, book to market ratio, the size, so market capitalization, okay, so earnings per share, okay, EBITDA, etc., etc. Okay, so maybe you have learned all of these terms from finance, but if you didn't, don't worry about that. Okay, this is not a finance lecture after all. This is a time series lecture. So the main important thing is we need to carry out dimension reduction because P or Q or both P and Q are large. Okay, so we want to reduce this to a more uh, reasonable size so that we can handle any time series manipulation, forecasting, uh, um, um, time series model estimation, etc. Okay. But I will not talk about the generalization of armor model to matrix, okay? Because these kind of models are still quite new, actually. All right. So I would say, so I hope everyone is still seeing me. Okay. So if you don't, please let me know in the chat or with some. Please have a shout to let me know that something doesn't follow. Okay. So XT follows P by Q matrix, and our sample size is actually again capital T. So in our economic example, T usually maybe 100, 200. If there's a year of data, maybe 200 something. So it's not too much compared to a matrix time series. So even one time at one time point, your number of time series you're looking at is P times Q already. Okay, so this usually can be large. So the matrix factor model. So usually it's given by, so again, xt, and then we need to have decomposition into just like a factor. So we decompose it into certain loading matrix and factors. Okay. And we decompose it linearly again. Okay. Uh, as I explained in last time, so all these uh, factors are actually latent. Okay. So decomposing it linearly, actually, we do not lose too much generality. At the same time, facilitate interpretation. Okay. If some of the factors are known, then you have much more flexibility to play around, maybe some linear model, etc. First of all, there's an alpha. This alpha is matrix. Of course, it's a P by Q matrix. Okay. So it's a constant. Plus this time, let me finish writing this first. Okay. And then plus an error matrix ET. So what is the common component? When it's a factor, the common component, remember in a factor model, so we talk about factor loading matrix B multiply with a factor of factors ft. Okay. Well, this time there are two factor loading matrices. Okay. One is the row factor loading matrix. So this is what we call the row factor loading matrix. And its size is, let's say, P times KR. So KR stands for the number of factors for the row. Okay. So let's continue with the example of you have different countries for the rows and different macroeconomic indicators in the columns. Okay. So KR is the number of factors for the countries, basically. Okay. R stands for row. Okay. And how about B? B is the column factor loading matrix. And what's its size? Its size is Q times KC. So C stands for column, of course. So KC is the number of factors for the columns. Okay. So in our example, so can we find number of factors, a certain number of factors that actually can summarize country size of variation for the time series data? So perhaps we can find KR number of factors. Perhaps these different countries can actually be summarized to just one factor. Perhaps you're looking at G7 countries, so you can summarize these G7 countries into just one index, just one factor. Can summarize these G7 countries different dynamics in the macro or macroeconomic indicators. After all, they move very closely. Yeah. And at the same time, so you have the column factor loading matrix. Okay, B. Remember that's B transpose. Okay, that's not a typo by mistakes. Okay, so it's A times FT times B transpose. All right. So B itself is Q times KC. So B transpose is KC times Q. Okay. KC is the number of factors for these different economic indicators. After all, economic indicators perhaps have some overlapping of what they're actually measuring. Okay. So perhaps for if you one of these is measuring GDP, then perhaps other indicators like consumer price index will likely be very much correlated with the GDP. So they're basically measuring something in common. So perhaps these micro or macroeconomic indicators can be collapsed into summarized into just several factors. Okay, so I have a big uh, uh, economic indicator index to summarize all these different factors you're considering. All right, so that's the idea. So this matrix kind of factor model, uh, in this sense, so usually we will have a row factor and column factor. Okay, so they preserve the meaning of the what's the meaning for the row for this data and what's the meaning for the column for this data. All right. If you have any questions, please let me know. Okay. So otherwise, let me continue. So let me write a little bit more down there. So what is FT in between? Now A is the row factor loading matrix and B is the column factor loading matrix. So what is FT? So FT is the num factor matrix. And the size is, of course, KR times KC. Okay. So the total number of factor time series we're looking at is actually KR times KC. Okay. So total number of country factors times the total number of uh, column factors. Total number of country factors times total number of economic indicators factors. Okay. In our example. So total number of factors. Total number of factors is then, of course, KR times KC. Okay. So usually KR and KC, we don't expect them to be large, maybe one or two. So even KR equals KC equals two, then that means there are four different factors. If you remember in our last lecture, we talked about finance. So usually there are only one or two factors. One is the market factor, another is the sector factor. So here, we'll expect a little bit more. After all, you have rows and columns representing quite different things. Okay, therefore you need more factors to really describe the majority of the variance of the data. Okay, so that's the idea. Any questions? So, okay, let me try to uh, look at the lecture notes with you. Okay, so let me open the lecture notes first. ST418. Now I know I need to stop share and then share the lecture note. Okay. Lecture note. Wow. These words are so small. Okay. So this is a lecture note. And so this is what I'm talking about is of course, the last chapter, chapter 5. Okay. So you have a multi-factor model, which we talked about last week, and some differentiation technique. And if you worry about differentiation for this matrix factor model, so do we need to differentiate with respect to a matrix this time? The answer is no, okay? I'll only talk to you conceptually how to estimate this, okay? So far less technical, actually, for the matrix factor model. Exactly because I don't want to go into too difficult territory mathematically, okay? Now, so we basically start from chapter 5.2, matrix factor model. So I've also demonstrated plotting of these 16 different time series, which is 16 of the time series from the 10 by 10 uh, portfolio return example, which I've demonstrated to you last lecture. Okay. So all these are actually I have two very recent paper. Actually, I have already three or four different recent papers about this matrix vector model. Okay, or even tensor vector model. So if you don't know what tensor is actually higher order high dimensional objects. Matrix is order 2 tensor. A vector is an order 1 tensor. So order 3 tensor, yeah, it's a cube, rectangular object. Order 4 tensor, yeah, I cannot even draw that, okay? So there are higher order tensor. So these are basically tensor analysis for time series, tensor time series. So this is only people starting to analyze this over the last decade, okay? And I would say still in a very young phase, unfortunately. Okay, so because it's really difficult to find really satisfactory summary. So it's basically a more case by case basis in the past. So nowadays, so we have a little bit more systematic analysis like this matrix vector model. Okay, so this is actually section 5.3 I was talking about. Okay. So equation 5.41 show you the factor loading matrix A and factor loading matrix B. So how do we actually estimate these different factors? Okay. How do we estimate the model, by the way? Okay. So that's what we will talk about now. So let me stop share and then share back the screen here. So I'm going to export this. Uh, So that's page one, I think. Okay. Okay, good. So how do we estimate this factor model? So that's the second part of what I want to talk about. So it's the estimation. So to estimate, first of all, alpha, we obviously want to use alpha hat equals to x bar, okay? And x bar being the mean for this matrix data, okay? So alpha hat is also P by Q, okay? So it's basically individual mean for individual element in the matrix, all right? And to reduce the difficulty of our estimation procedure, this is why I'll consider ET to be exactly zero here, okay? So if ET, if there's no error, if we observe pure mean plus this low rank matrix, which is A, FT, B transpose, how do we decompose it? How do we decompose into factor loading matrices and also the factor matrix FT? Okay. So first of all, you want to construct this X. Okay. So this is a P by Q centered matrix X1 minus X bar. And then we put all the other data at different time points together. Okay, like this. All right. So this is a really, really huge matrix, right? So it's P by T times Q, right? Each one is P by Q. There are T of them, just to both side by side together. So the number of columns is Q by T. And we have this. So if we use our, if we use our factor model, so this x1 minus x bar, so we also need to do one thing. Okay, so suppose also, which will usually be satisfied. Suppose alpha hat is also very close to alpha. We don't want to be bordered by this alpha. So if alpha hat is very close to alpha, x bar is very really close to alpha. So alpha will be eliminated, ET will be zero. What you're left with is this matrix, right? This is F1 minus F bar times B transpose all the way down to A times F capital T minus F bar times B transpose, right? Remember, we're still dealing with matrix, okay? So with this big matrix, look, we have A and B transpose are common to them, okay? So you may be tempted to, okay, take out A on the left-hand side, which is a legitimate operation, by the way. Mm. So it's a legitimate operation. There's no B1 here. What am I doing? Okay. So is this big matrix, very long matrix? Actually, we can take a factor A out on the left-hand side. So you may have a similar question. Well, can we take B transpose out to the right-hand side? Well, the answer is of course not. Okay? Of course not. You need to think about that. If we take B transpose on the right-hand side, so basically the size of the matrix changes. Okay? But if we take on the left-hand side, then yeah, the size of the matrix is okay. A is P times KR, remember. Or the F1 up to FT is KR number of rows, okay? So A can be multiplied to this big matrix. But if you take B transfer out to the right-hand side, they cannot be multiplied together, actually, okay? So this matrix is similar to if you have done the exercise for factor armor model, okay? So taking covariance of matrix times a factor. So when you take out matrix on the left-hand side, it's fine. For the right-hand side, you need to take it as transpose, okay? So here, you can't even take out the B transpose at all. So there are lots of rule of thumbs, okay, to help you remember. But here, usually the factors are on the left-hand side, so it's fine, okay? If you put matrix together, row column by column, okay? If you stack them together by a column matrix, so x1 minus x bar, below that is x2 minus x bar, then it's a different story. Then is this time B transpose to be taken out on the right hand side rather than A. Okay. So, but remember this, okay? Remember in what we are doing and what in the lecture notes is doing. We are placing this x1 minus x bar, x2 minus x bar side by side, okay? So the final matrix is P times very, very large number of columns QT. Okay. Then we can take out A to the left hand side. Okay, so what's the implication of taking A to the left-hand side? Well, if we can formulate the matrix X which has A on the left-hand side, then X transpose X is what? Is sandwiched by A. Is A times this big matrix. I don't care what that is for now. Multiply with its transpose and then multiply with A transpose, okay? So it's sandwiched by A and A transpose, X transpose X. So how to estimate A? So therefore, we can estimate A by the KR eigenvector. So E vector stands for eigenvectors, okay? Of X transpose X, okay? Of X transpose, sorry. Not X transpose X. So I need to be really careful here. So it's X transpose, then it will be sandwiched by A, okay? So the KR eigenvectors of XX transpose correspond to the largest KR eigenvalues. All right. And if you have done some reading, so okay, this is a little bit different from what we have written in the lecture note, but of course it's equivalent. So in the lecture note, I talk about, so this is equivalent to the first KR left eigenvectors of X, okay? All right. So left eigenvectors, basically, it should be singular vectors, okay? Yeah, I shouldn't, yeah. Maybe I should use back singular vectors. So it's basically singular value decomposition, SVD, okay? So remember every matrix, so we can find the SVD, right? So any matrix A, we can find an SVD like this, singular value decomposition, okay? So you want to find the left-hand side is now A, okay? So it can be represented by the K left singular vector. So basically correspond to U there, okay? For this big matrix X. All right. So we can find the left singular vectors of X correspond to its largest singular values. So I should write it down. Correspond to the KR largest singular values of X. Okay. Now this coincides with what we talk about in the lecture. Okay. So let me add this before I change to another page. So how do we estimate B? How do we estimate B? Well, B is similar. So if we define now X is like that, right? Side by side. This time we really define XV to be something stacked together. So it's X1 minus X bar, X2 minus X bar, up to xt minus x bar. This time we really stack them together vertically rather than horizontally. Then what do we have? We have xv transpose will then be, so I define this, xv transpose will then be x1 minus x bar transpose up to xt minus x bar transpose. Again, if we ignore alpha and the uh, error matrix ET, this will be what? This will be B. This time multiply with this big horizontal matrix, F1 minus F bar transpose A transpose. All the way up to F capital T minus F bar transpose A transpose. All right. So you know how to estimate B now. To estimate B, well, let me write it in singular value fashion, okay? So you basically, therefore, can estimate B by the first KC left singular factors. I think in the lecture notes I still call them eigenvectors. Okay, singular eigen. Okay, yeah. Of XV transpose. So singular vectors certainly correspond to singular value decomposition. Okay, eigenvectors correspond to the eigen decomposition. Or first KC E vectors of this times its transpose, okay? We have XV transpose on the left-hand side and then multiply its transpose, that's XV. So on the upper part, we have X transpose, and here we have XV transpose XV, okay? And when I talk about first singular vectors, first KC eigenvectors, it corresponds to, what I didn't say is it corresponds to the largest KC eigenvalues, okay? So uh, I will only state this with a ambiguity arises here. I don't think there's any ambiguity here. Okay. So the first KC eigenvectors, of course, correspond to the first largest KC eigenvalues. Okay. It's always correspond to the largest. Okay. Largest, of course, contains the most information. All right. So any questions? So I think I spent really long time here. Um, but of course, finally, we can estimate FT. So your FT hat here will then be what? If you have A hat and B hat, then FT hat will be A transpose XT times B hat. Okay. Imagine your XT contains A hat transpose. Imagine your XT only contains this should be minus X bar, of course. Yeah. Imagine your model for XT only involve uh the signals, so the alpha as well as the common component A, F, T, B transpose. Okay, ET is 0. Then after taking out the mean, what you're left with is just A, F, T, B transpose. Okay. Here A and B, of course, well, uh you have already basically given uh the unset restriction. Remember, in a factor model, factor loading matrix is orthogonal, having orthonormal columns. So here, by taking singular factors, eigenvectors, we'll also assume that they have orthonormal columns. Okay, and therefore multiply with A hat transpose and B hat. Of course, we'll cancel out the A, F, T, uh, B transpose. So the FT is actually multiplied with A hat transpose on the left hand side and B hat transpose on and B hat on the right hand side for XT minus X bar. Okay, so that's F hat T. Okay, so it's basically uh, A transpose times A F T B transpose times B. We'll go back to FT. Okay, because A transpose A and B transpose B are both identity. All right. So we skip all the least square estimation. You can actually derive this very rigidly with very solid mathematics. Again, go back to these least square estimators. So they are actually, after all, still least square estimators. Okay. So you can try it. Okay, but inevitably you need to differentiate with respect to matrices. Okay. If you're really interested in the mathematics, let me know. Okay. But here, I only talk about this very conceptually. All right. So, there's a name for this. So after talking about this name, I'll give you a 10 minutes break. Okay. So these are what we call the higher order singular value decomposition. In short form, HOSVD. So not only for matrix time series, tensor time series, people talk about HOSVD, so you know what that is, okay? So HOSVD is, we're talking about basically a factor model for these high dimensional objects. So higher order SVD, okay? And all these are HOSVD estimators, okay? So if I ask you the form of the matrix factor model and then do HOSVD, describe the process of HOSVD, so you know what to do, okay? So, uh, so you can present this conceptually. So if ET is 0 and alpha is estimated perfectly, so what you're left with is just the common components. So how do we estimate B and A and F? Okay, so this is how we do it. All right. So for now, I think okay, I'll give you 10 minutes break. So if you haven't completed the survey, so try to do that. Okay. So I don't know if it's still open, but try to finish the survey because our response rate is quite low across the department actually. So I will try to open the survey again. So please try to finish that. Okay, so you'll receive email notification. So I'll give you 10 minutes break. So please come back at 2:03. Yeah, 3 minutes past 2 o'clock. Okay, so I'll see you later. But hopefully you can try to complete the survey. So I'll open again. Let's see. Okay, I've sent the email. So if any one of you haven't completed the survey, so please try to complete the survey. So thanks in advance. Okay. So please come back at after 8 minutes. Okay.
Sorry, you're muted. We can't hear you.
Thank you, thank you. That's very.
Welcome.
Thank you, thank you. Okay, so let me do this again. So we have just talk about the actual SVD, the higher order singular value decomposition. So how do we find the factor loading matrices A and B as well? Essentially, you can see that we are basically summarizing a high dimensional object P times Q number of time series into just KR times KC number of time series. Basically down to factor matrix FT. Okay. At the same time, we respect the structure of the matrix time series because a P by Q matrix now is summarized to another matrix as well, but it's much smaller size. It's just KR times KC. Okay. So basically, through summarizing the row dynamics, okay, into KR number of them, and then column dynamics into KC number of them. All right. So, what else do we need to know about this matrix factor model? Well, of course, people have talked about inferences and so on, and AR model or um, MA model, which is similar but respect the matrix nature of the time series. But we're not talking about those. All right. So we continue to focus on this matrix factor model. But how do we improve on the estimation? All right. So on this page, on this last top, one of the last topic, it's the second last topic, basically. So we'll talk about projection estimation. So what do we mean by projection estimation? So, well, you have two matrices A and B, actually, right? So if we know A in advance, let's not ask the question, how do we know A in advance? Well, perhaps we have completed the higher order SVD in the first place. So we have an estimator of A and an estimator of B. So we know a matrix A hat, which is close enough to A in advance. So let's assume that we know A in advance in this model. The model again is xt equals to alpha plus AFT B transpose plus ET. Okay. So what are we doing? Then we project in the direction of A for the rows of xt. So sounds like word salad, basically. What exactly do we mean? We mean that we basically means multiply a projection matrix in terms of the column space of A. So if you have done any least square estimation, so this is the projection estimator, right? Okay. So if you want to project into the direction of A, this is the projection estimator. So we on the left hand side. So for the rows of A, we multiply on the left hand side. And well, if A is such that A transpose A is identity, So identity with size KR. Okay, so that's exactly what the HOSVD estimator has as a property, right? A hat exactly has this property because they are eigenvectors after all. So we are but just basically multiplying A transpose on the left-hand side. So A transpose XT, let's say minus X bar, will be very close to, let's assume that, again, alpha here, uh, let's not. We don't need to do any approximation here first. So let's retain that alpha there. So let's consider what A transpose XT is. It equals to A transpose alpha plus A transpose times A. Well, that is identity, right? So you only have FT multiplied with B transpose and then plus A transpose times ET. The main point I want to draw your attention to is the size of A transpose ET. The original size is P times Q, remember? It's the same size as the matrix XT. Now A transpose ET, what is its size? A is P times KR matrix, so A transpose is KR times P matrix. So a KR times P times a P times Q matrix is KR times Q matrix. Compared to size of ET, which is P times Q. So if we really have information on A and we do, this is called a projection, okay? A projection of XT like this, then what you're left with is a very similar model, okay? But the error has a much, much smaller size. If P is 100, Q is 100, okay? So original size of the error is 10,000. So 10,000 errors in a single ET. If KL is just one, okay, as you have seen in the portfolio return, so later on we'll see that. So major, in all likelihood, so there's only one factor. So perhaps there's a uh, one factor that represents size, one factor represents the book to market ratio in the portfolio return data. Okay, if KL is just one, Q is 100, so 1 times 100 is what? 100. Okay, so the size of this A transpose ET is just 100 compared to original number of errors is 10,000. Okay, so 100 times smaller. So if you use this model to estimate B and FT, well, it would be leading to a much more accurate estimator, as you can imagine, right? The size of the errors, of course, it depends on now from 10,000 number of errors to 100. So are these 100 errors much larger, statistically speaking? Well, this is one of the exercise in exercise 11, okay? So in exercise 11 to question 2A, I exactly asked this question. So after projection, what's the distribution of the errors in this A transpose ET if ET itself have IID normal data? Let's say they are IID standard normal. What's the A transpose ET? What's the distribution of the errors in the elements in A transpose ET? So you find that in the end, well, the size, statistically speaking, won't be increased at all. They are still standard normal, but the number of errors is much reduced, 100 times reduced. With the example I talked about, from P equals to 1, reduced to KR, P equals to 100, reduced to KR equals to 1. So 100 times are smaller for the number of error terms. Each error term with size, statistically speaking, stays the same. Okay, so projection is a very powerful method if we truly know have a valid projection direction, of course. Okay, so in practice, hopefully, our HOSVD estimator are accurate enough so that we can use a hat from the HOSVD to do this kind of projection and estimate the rest of the parameters again for this matrix vector model. Okay, so let's continue to estimate B. So to estimate B from the above, we basically is doing this. We basically want to stack the data and then take transpose. Okay, so we stack the data and then do transpose. This basically is x1 minus x bar transpose times A. And then x2 minus x bar transpose times A all the way up to xt minus x bar transpose times A. So this will be close to again, similar to HOSVD, it's only conceptual. We assume ET is negligible, okay? So it's close to B multiplied with all the F1 minus F bar transpose all the way to FT minus F bar transpose. So therefore, we take B hat as the KC left singular vector of this matrix, of this projected matrix, okay? So here we assume A is known, okay? Now how about B? Well, B is similar. Sorry about that. So it's very similar. Let me it's long enough. So let me export this first. So I've demonstrated the idea, okay? So both, of course, both A and B are unknown. But we can use A hat and B hat from the HOSVD procedure, from the higher order singular value decomposition, as initial estimators. So what do we mean by initial? Okay. So our first step will be, remember the last page, we take this matrix up to xt minus x bar times a hat. So hopefully this matrix, we can take the first KC left singular factor as a B1 hat, okay? Now after this, then define this time we go back to horizontal. You use B1, the newly obtained B1 hat to do this procedure. So this time we project up from the right-hand side, okay? The idea is to eliminate B from the matrix factor model. X1 minus X bar, if ET is close to 0, X bar is very close to alpha, what you're left with is AFT times B transpose. So A times AFT B transpose times B, what you're left with is just AFT, okay? So hopefully what you're left with is A times some big matrix, okay? So define this. So A should be able to be taken out on the left-hand side if everything goes smoothly. So just take is KR left singular vector as A1 hat, okay? So from our initial estimator A0 and B0, we can project it, obtain estimator of B1, project again, obtain estimator for A1. And then obviously, well, hopefully A1 and B1 hat are improved estimators. Then we can iterate this whole procedure, okay? Replacing A1 hat as A hat, B1 hat as B hat, and repeat the procedure again, okay? So we can iterate this. Well, basically A1 hat will goes to A hat, and then the B1 hat will go back to B hat, and then go back to the top of the page. Until convergence, okay? Or if you want to know how many iterations you have done, so from A1 hat at B1 hat, you will obtain A2 hat and B2 hat. And then from A2 hat, B2 hat, you obtain A3 hat and B3 hat, and so on and so forth, okay? So you can keep track of how many iterations you have done. Until convergence, what do I mean by convergence? Well, perhaps something like this. Perhaps something like A hat I plus 1 minus AI hat. So the ith iteration and the I plus first iteration will have a distance, maybe not larger than a certain preset error, something like that, okay? So if you have done other statistics program or projects, so maybe you would have encountered these kind of very practical stopping criteria for iterations. Okay. So you usually look at how many changes, are there any big changes for your estimators? Well, in a lot of deep learning algorithms, so perhaps the gradient is not too is close to flat. Okay, a lot of times deep learning algorithm dealing with very complex functions. So a lot of times they're close to flat gradient, and perhaps these kind of stopping criteria may not be good. Okay, so maybe we need to check something else. But for this one, so I think this stopping criteria will be reasonable. Okay, for small epsilon. So what we have a name for this. This is called again higher order. This is called higher order orthogonal iteration. So the whole procedure also is described in the lecture notes, and the whole name is HOOI. Okay. So if you try to study this matrix factor models, uh, more often than not, so you would have seen this HOSPD or HOOI. So they stand for these two terms: higher order singular value decomposition and higher order orthogonal iteration. Okay. So any questions? Okay. So let's go back to, let me export this first. This should be the fourth page. So let's go back to the lecture notes and see some practical example. The lecture note. So I'm showing you the exercise 11 because as I said, question 2 is exactly for this factor model. So you need to remember the procedure for HOSVD and also the concept of HOOI and know how to describe these two procedures in terms of how to obtain these estimators. What matrix are you setting using the data, using your observed data, and how do we obtain these estimators? Okay, so you need to be able to describe both these procedures. And with respect to what I talk about after projection, the error term will be much smaller. The number of errors is much smaller. How about the size of each element in this error matrix? So are they still the same size? Well, at least question 2A answer the question when ET are normally distributed. Okay. So hopefully this may convince you that this projection procedure leading to HOOI is really a sensible one. Okay, so it usually will lead to much more accurate estimation of these factor loading matrices. All right, and then let's look back at the lecture notes. Now this is 5.4.1 in the lecture notes. So for the HOOI. So hopefully I have explained that clearly. So I didn't even include XBAR because my original model doesn't have an alpha. So if you have an alpha, a fixed constant in your original model, of course you need to demean it first. All right. So therefore minus XBAR as in the handwritten notes. Okay. Um, so I have described this procedure. I only have described how do you iterate A and B. So after obtaining the HOI estimators for A hat and B hat, so they converges hopefully, then FT again will be obtained by the same formula. All right. If you have alpha, then it's A hat transpose times xt minus x bar. Here I use yt minus y bar times b hat. All right. Why do I change the lecture note? Is because I want to talk about example 5.3. Very practically. Okay. So let me maybe make it larger. So how do we find KR and KC? Okay. Now remember, how do we find KR in the first place? Remember, we find KR as eigenvector of a certain product matrix, right? If your data matrix here, I use Y in the handwritten note, I use X, doesn't matter. So I constructed a matrix X, basically, a long matrix X, and then multiply with its transpose, then it's actually sandwiched by A. So it's A times the big matrix times A transpose. And then I can estimate A using the KR, first KR number of eigenvectors corresponding to its KR largest eigenvalues. Okay. So obviously, the eigenvalues in this XX transpose or here YY transpose matrix matters, right? So how about counting the number of large eigenvalues in this matrix? It's very akin to what we have done in the factor model. Okay, so we're basically doing eigen analysis, finding finding eigenvectors corresponding to large eigenvalues in the sample covariance matrix. Here we are doing the same thing. We are finding eigenvectors for YY transpose. Okay, according to how many large eigenvalues are there in YY transpose. So to find KR naturally, we're looking at how many large eigenvalues are there in YY transpose. And that's for KR. For KC, well, we do Y transpose Y. Okay. Remember, how do we find B? We basically stack the matrix first and then multiply its transpose. That's basically Y transpose Y. Okay. So for finding case C, we find how many eigenvalues are large in Y transpose Y. Okay. So all these are basically akin to the factor model, finding number of large eigenvalues in the sample covariance matrix. Okay. It's just the difference is just that we have two sample covariance matrix now. It's YY transpose and Y transpose Y. Okay. Okay. They're not exactly sample covariance matrix, okay? But yeah, it's basically a very generalized kind of matrix. And we can look at the portfolio return example. Okay. So in portfolio returns example, if I'm not going to run this here. Okay. So try to run this in portfolio returns, portfolios.r. I've run the first part of this script in the last lecture, remember? Okay, to show you I can stack the 100 portfolios, return together, and try to do a factor model. Okay, it's still fine. After all, 10 is not a very, very large number. Okay, relative to the sample size. In the end, no matter I do Y transpose Y or YY transpose, so the upper plot is YY transpose. Okay, square plot basically means I plot the eigenvalues from largest to smallest. That's square plots. Okay. So you can see for YY transpose, so Y transpose Y both, maybe 1. Okay. That's quite obvious, to be honest. Okay. From 2 onwards, is many things are very similar to the others. Okay. So perhaps KR and KC all equals to 1. So in the end, FT, the matrix KR times KC is just a scalar. Okay. So it's one factor model for both. All right. So looking at this, this is quite conclusive actually. That's just KR and KC are both equal to 1. It's not really um, unheard of in finance. So usually the market factor dominate all the signals. So what people do for, especially for finance data, maybe they take out obvious market factor first. So they estimate the market factor and then we move it from the data and then try to do this eigen analysis again to further try to find if there are any other weaker factors, so to speak. Weaker factors, I've talked about that. Some factors perhaps not pervasive. Some factors perhaps only affect a certain sector. For example, in this particular example, some factors maybe only affect certain book to market ratio, maybe certain size of stocks. Maybe if the stock is too small, then this factor it doesn't really apply. Something like that. Okay. After we moved in the market factor, perhaps we can find other much weaker factor. Okay, so this market factor is so strong, it dominates everything. All right. So that's basically all the topics. So you're left with just one topic. So I will talk about this. So let me write down the note. So we still have enough time, I think, to do that. Okay. Wait a minute. Let me share back the screen. So I think I exported that already. Okay. So that really is the final topic. Oh, that's page 4, page 5, yes. So restrictions of a matrix factor model. If you're really interested in the topic, if you look at perhaps other papers to see, matrix factor model, there are actually two main types. The one I introduced is one type, which we call Tucker decomposition for the common component. There's also something called CP decomposition. I can't remember that name. I can never remember these complicated names. Okay. So CP decomposition basically is a special case for a Tucker decomposition. Okay. So why do special case matters? Perhaps sometimes special case really free out our data to estimate important parameters. Okay. CP decomposition basically tells you that FT is actually a square matrix. At the same time, it's a diagonal matrix. Okay, that means all other FT on the off diagonal doesn't matter. Okay, so only diagonal. Okay, so it boils down to certain decomposition, but I'm not going to talk about that. If you're interested, so let me know. Okay, so I'm more than happy to fill you in the details. Okay, and introduce perhaps some papers for you to see if you're interested in this research direction. Okay. So you can see along the way in the lecture note, I introduced some papers which I recently wrote with my really capable students, Sitai Sen, who was GTA before. So now he's actually a senior research fellow in Bristol. Anyway, so what's the restrictions of a factor of this matrix factor model? Uh, what are the restrictions? I'm not talking about uh, the artificial restrictions we add to A and B. So A transpose A is identity, right? Also, B transpose C, B is identity. I'm not talking about these kind of restrictions that basically is identifiability conditions. Okay, I'm not talking about that. I'm talking about real restrictions of a factor model. So let's write down the matrix factor model again. So with matrix vector model, we have this form. So right hand side, they're all latent. So you need to basically decomposition of the data xt. Now, how to find alpha, A, F, T, and B? So we have done all that. Okay, so E hat estimator for E, the error is basically xt minus all these components. Okay, I haven't talked about that, but should be obvious. But the restriction I want to talk about is consider this factorization of xt. So vac of a matrix with q number of columns is actually this long factor A1 stacked with A2, stacked with all the A up to AQ, okay? So if originally you have a P times Q matrix, okay, then all these AI are of dimension P. If it's a P times Q matrix, right? There are Q columns, P rows, okay? So A1 has dimension P, A2 has dimension P, etc. So we are stacking all these P-dimensional column factors in a long factor, okay? So it's a P times Q dimensional factor, PQ dimensional factor. So that's fact of xt, okay? We stack the columns into a long factor, okay? Factorization. So fact of xt, something that you need to know. So fact of A plus B, of course, is fact A plus fact B. So therefore, your fact xt is fact of alpha. Remember, alpha is a constant matrix as well, P times Q matrix. So you can stack its columns on top of each other. So fact of alpha plus the fact of A, F, T, B transpose. And then plus the fact of ET. Well, no problems here. Well, we can actually simplify the middle part, so to speak. And B and A can actually be taken out from the fact. So there's a general formula. Let me write it down first, okay? So it actually equals to B times A, Kronecker product, times FT, fact of FT, plus fact of ET. So what is the Kronecker product? So where B times A is defined as, so this is basically the definition of Kronecker product. So this B11 times A, B11, B12, they are all scalar elements, okay? So B12 times A, the B1, I do not know, B1Q, KC, right? KC. No. Times A, and then it's B, is Q, right? Q1 times A, BQ2 times A, all the way down to B, Q, KC times A. Remember, B is Q by KC matrix, right? That basically is a general definition of a Kronecker product, okay? Kronecker product of two matrices is basically the second matrix multiplied with each element in the first matrix. Basically, it becomes a real really large matrix. What's the size now? The size basically is if B is Q times KC, right? A is so is PQ times KR KC. So it's a really huge matrix. Okay. It's a really huge matrix. But what is PR times KR KC? Now remember, in matrix factor model, there are KR times KC number of factor time series, right? So KR KC represent the number of time series in fact of FT. And PQ is the, of course, is the original stacked dimension of the vector. So XT contain PQ time series. You stack them to one long vector. Of course, the dimension is PQ. Okay. So if you think about that, you think about the if we model fact of XT using what we know about factor model, then the model is what? Let me leave it. Okay. Then the model actually is this. Okay. So vec of xt equals to perhaps a certain factor mu plus a certain factor loading matrix, let's say uh, U multiplied with uh, let's not write fact, okay. Let's write FT. So I'm basically conforming my notation to the factor model, which you have done in the last lecture. Okay, so plus an error ET, where your mu has size PQ, U has size, that's the most important thing. U has size PQ times what? If you have, let's assume that KL times KC factors really is doing the job, so it's KL times KC, right? So FT do correspond to vec of FT, okay? So that's KL times KC times 1. So that's the two main object. Okay, so this is general matrix U, general factor loading matrix U, PQ times KL KC. So what's the compared to the fact of XT, which is derived from a matrix factor model. So you can see that matrix factor model has a natural restriction. This natural restriction is when we factorize xt, then we can see that. This natural restriction is the factor loading matrix now has a Kronecker product structure. So let me write that down. Hence, matrix factor model induces a Kronecker product. Kronecker, by the way, that's how it's spelled. Kronecker product structure in the factor loading matrix. In the factor loading matrix of the model for the VAC of XT, of course. So compared to the VAC of XT, which we treat it as completely just a factor, okay? We don't respect any matrix structure in the original data, then you can have a very free factor loading matrix U of dimension PQ times KLKC. So factor structure basically is retained when the factor loading matrices are of Kronecker product structure. Okay. So this Kronecker product structure has a very close connection to matrix factor model. All right. In this Tucker form, or at least. Okay. So how do we test it? Well, this is just question. So you can see the lecture notes. So in the end, I put out a link. So actually, my student very brilliantly lead the project. Okay, so he derived a test, not only test for tensor, not only test for matrix factor model, but tensor factor model as well. So a test on how if uh, matrix factor model actually is enough. Okay, enough means when you factorize xt, the factor loading matrix approximately actually of Kronecker product structure. Okay, if it's wildly violated this assumption, so the factor of VAC of xt doesn't really have a Kronecker product structured loading matrix, then you are basically rejecting this null hypothesis that the matrix factor model is okay. Yeah. But well, of course, the test is far too complicated for this course. Okay. So I'm just making you aware of this fact. Okay. So there's a natural restriction for a matrix factor model compared to factorized data, a factor model, general factor model for the factorized data. All right. So I think I have talked about all I can for this course. So once again, I'm really sorry that I have to uh, stay away from LSE on the last day, but um, hopefully this course has been useful to you. And hopefully you have learned some practical aspect of time series analysis as well, at, at least from the first half of the course, where when we talk about scalar time series. Okay, so have a happy holiday. So happy Easter, and I know that you undergo a lot of revision for a lot of courses. So good luck with that, and don't don't forget to relax yourself. So even under intense pressure of studying, finishing projects, etc. Okay, so good luck, and I hope I'll see you guys or in the future. I hope you have a really bright career ahead. Okay, so for those students who have a Group 1 seminar, so I'll see you guys later. Okay, so I'll stop the lecture here. Okay, good luck. Bye bye.